So in the last video, I talked about the chapter 6, which is the second law of thermodynamics. And now in chapter 7, I'm going to talk about this process called entropy and its different processes and its relation to the second law of thermodynamics. So now I talked about the inequalities in the second law of thermodynamics, and now to begin, I'm going to talk about an important inequality in this chapter, which is the Clausius inequality. It states that the integral of the difference in heat transfer over the temperature cannot be greater than 0. It should always be equal to 0 or less than 0, and it is applicable to all cycles, whether they are reversible or irreversible. And for reversible cycles, we have that they're same in magnitude, but they're opposite in sign. But since the work cannot be a negative quantity nor a positive one, so this inequality should always be equal to 0. So that's for the Clausius inequality. So now, to start this chapter, entropy is an extensive property. So we have this formula that states that the change in entropy equals to the difference in heat transfer over the temperature. So now for these processes, we can state that we can state two different stages. So state 1 can be a reference state. So our state 1 should be equal to 0, and state 2 is the state at which entropy is to be determined. So the change in entropy equals the state 2 minus the state 1, and this equals the integral of this difference in states of this formula. So we need to know the relation between the heat transfer and the temperature, and in most cases there's tabulated data for entropy. So in our property tables we can look for the entropy of the given temperature, and there's specific value for its temperature. So we determine our reference state. For example, we can say that our 25 degrees Celsius is our reference state, and the entropy that we should determine, it's the other temperature we want. It's like the enthalpy. So now for internally reversible isothermal heat transfer processes, we are going to have this formula, which is the one that we stated here, but now we have initial temperature, and the initial temperature is a constant, so we can do only the integral of the reference state of the changing heat transfer. So it is useful for determining the entropy changes of thermal energy reservoirs that can absorb or supply an indefinitely heat at a constant temperature. So now for heat transfer, when we have a system and the heat transfer goes to the system, we are going to have an increase in entropy. But if the heat transfer is from the system to another system, we're going to have a decrease in entropy. So the only way we can have a decrease in entropy is to lose heat. So now the increase of entropy principle. We have irreversible and reversible processes. So for irreversible processes, the entropy change of a closed system during a reversible process is always greater than the entropy transfer. And for reversible processes, this change is these two quantities become equal. And therefore, we are going to have an entropy generation that for example, a change in entropy of the system equals this formula, as I said it before, but we are going to have an entropy generation. But it depends on whether we have a reversible or irreversible processes. So the generation is going to be greater than 0 if we have an irreversible process. We are going to have no generation if we have a reversible process, but we can never have negative generation of entropy. And this is called the increase of entropy principle. So now remarks about entropy. As I said it in the chapter 6, the processes occur only in a certain direction. It depends if we have a reversible process that cannot go back to the initial state, or a reversible process, but there's only going to be a path. And in the case of entropy, there's no such thing as a conservation of entropy principle, such as the conservation of mass, because entropy depends on the substance, and it's as an extensive property. So there's a entropy